Hi everybody, it's Cameron here. Today we're going to be looking at rates and equilibrium. We're going to be looking at how temperature, pressure, concentration and catalysts all affect how quickly a reaction happens, the rate of the reaction. We're also going to be looking at what reversible reactions are and how they can also be affected. Okay, so let's start it by looking at what can affect the rate of a reaction. Okay, we're going to look at the phrase collision theory as well. Okay, so it starts out with if the reaction is going to have sufficient energy. Previously, when we talked about endothermic and exothermic reactions, we talked about the activation energy. Okay, if that activation energy is not reached, that means that collisions between particles, when particles come into contact with one another, or if particles are being broken apart, okay, this will not occur if there is not enough energy. They'll bounce off each other or they'll remain together. Okay, so sufficient energy is required. This is going to be in the form of heat energy. Okay, so with more heat, the particles are going to vibrate more and they're going to move more and collide into each other more. Okay, so increase in heat can sometimes lead to an increase in the rate of reaction. We know though that if it's an endothermic reaction, it's not the case. Okay, so but it still has, endothermic reaction still has a activation energy though, so that's important to remember. Okay, then it comes down to the surface area. Okay, so how big are these particles that are going to be coming into contact with one another? And when I say big, I'm not meaning that bigger particles have more chance. I'm saying how much surface do these molecules have to react with one another. Okay, if you look at medicine, there are some pills that you have to take by just swallowing them, others that they say you should crush, okay, in your mouth, you should chew them. Now, why are they saying chew them? Okay, it's for the same reason that some pills come in a powder or powder in a capsule. Okay, if the medicine needs to work quickly, okay, it's in a powdered form so that it can react quicker. It doesn't have to dissolve slowly through this big pill. It can have instant contact with as much of the chemical as possible. You see, so an increase in surface area means more chemicals or more particles have access to making contact with one another. Okay, next one is concentration. Obviously, if you have more particles in a certain area or in a certain solution, then they are more likely to come into contact and react with one another. Pressure is another one. Okay, so pressure means that there's going to be less space for these particles to move around, and therefore they're going to come into contact with each other more often. Okay, but with an increase in pressure, then there's obviously going to be less contact. Okay, and finally a catalyst. Okay, so when we were talking about endo and exothermic reactions, and I think in the next slide we actually have a graph of it, catalysts are going to lower the activation energy required for the reaction to take place. Okay, so this can sometimes be for economical purposes, okay, as well as functional purposes. Sometimes you don't want a reaction to take so long, you just add a catalyst and it'll happen a lot quicker. Okay, or you don't want to heat up the reaction to incredible temperatures, you can put in a catalyst and it's going to decrease that activation energy. Okay, and that will speed up the rate of the reaction. But it's important to remember a catalyst does not affect the product or the outcome of the reaction. The reaction will just happen quicker and sooner. Okay, so yes, here again we're looking at a catalyst. Okay, how they work is they are going to be decreasing the activation energy, but they do not affect the reaction. So if a certain amount of heat is given off in a reaction, that amount of heat is going to be the same, okay, but the amount of energy required to start the reaction is going to decrease. This will lead to more effective collisions and therefore increase the rate of the reaction. Okay, so we can use lots of different materials as a catalyst. A catalyst is going to provide alternate pathways for a chemical reaction to occur. Okay, And again, we're going to usually use it in a pellet or powdered form, okay, because it increases surface area that the chemicals can use, okay. And again, it's okay because the pellet or powdered form will remain in that form. It won't be used in the chemical reaction, okay. That's why it can stay there, is a powder, and it can then be filtered out. It does not change the product of the chemical reaction. Okay, it's just going to increase the speed at which it occurs, the rate of the reaction. And for different reactions, we use different catalysts. Okay, so how do we measure this rate of a reaction? Okay, so there's different methods. When it comes to the actual reaction, like the physical chemicals, what we can measure is the decreasing mass of the reactants, okay, and the reaction mixture if there is a gas being produced. Okay, we can also measure the increasing volume of the gas given off, usually using a gas syringe. Okay, or we can measure the decreasing light that might be passing through a solution. This is usually when a solid precipitate is being formed that won't dissolve in the solution. It will become cloudy. Okay. The calculations you can use, the mean rate of the reaction is equal to the quantity of the reactants used divided by time, or the amount of products produced divided by time. Okay, both will give you the rate. When we're looking at graphs, however, it is going to be the gradient of the graph that will give us the rate of the reaction. Okay, so the change in y divided by the change in x. Some people also say rise over run. That's the gradient. Okay. If it is, however, an exponential graph, okay, you can work out the gradient at a certain point by drawing a tangent line. Okay, I will attempt to draw it here. Okay, so let's say it's something like that. I can work out the specific rate of a reaction at this point by drawing a tangent line. Yeah, that'll go through that point. Okay, and that tangent line is then, I can calculate the gradient of that and figure out what the rate is. Okay, so now let's look at reversible reactions. So there are some reactions that once a product is formed, that same product can go backwards in the opposite direction and form the reactants again. Okay, we represent this using these two arrows instead of just one. That shows a reversible reaction. Okay, now the thing you have to know about these reactions is that they are going to be opposite from one another. Let's say that the forward reaction, okay, from left to right is exothermic. Okay, energy is being given off. That means that if we have to go for the reverse reaction, it's going to be endothermic. Energy would have to be taken in. And this makes sense because if energy is given off by the reactants, to make that reactant again, that energy given off will have to be taken back in. Okay, so they're going to be opposite from one another. Okay, it's also going to be different pHs. Okay, so let's say that the forward reaction is acidic, the reverse reaction is going to be basic, and this is due to the amounts of hydrogen ions and hydroxides that will be present or being used up. Okay. Okay, so we look at now a dynamic equilibrium. Okay, so if you leave any reaction, initially the forward reaction is going to be happening. Okay, but then at a certain point, the reverse reaction is going to start happening. And when the rate of the forward and the reverse reaction is equal, then we say equilibrium has been reached. In the last slide though, we said, however, that those reactions are going to be opposite. Okay, exothermic for the forward, endothermic for the reverse. It can also be the other way around. Forward could be endo, reverse could be exo. Okay. So once these reactions reach equilibrium and we tweak, if we change the conditions of the environment, it can favor the forward reaction or the reverse reaction. Okay, and how we can do this is, I think we mentioned it in a previous lesson actually, when it comes to an exothermic reaction, if we decrease the temperature of the environment, it's going to be taking out that exothermic energy, okay, thus favoring whichever reaction is exothermic. If we increase the temperature, okay, that is going to favor an endothermic reaction, as it is trying to gain energy from the environment. Okay. Another way that we can adjust the equilibrium, we say, okay, is by adding the reactants or products. Okay, so once equilibrium is reached, if I were to increase the reactants, obviously then it's going to favor the forward reaction. If I were to increase the products, it's going to favor the reverse reaction, and that's going to happen more. Okay, until equilibrium is reached once again. But then it is kind of skewed. Okay. Another way that we can do it is by increasing or decreasing pressure. Okay, so an increase in pressure is going to favor the side of the reaction, either the reactants or the products, that has the most molecules. Okay, because those molecules are going to need to come into contact with one another to have those successful collisions. So if we increase pressure, we're favoring the side with more molecules. Okay. If we decrease pressure, we're favoring the side with less molecules because we're giving them space to be able to break apart. Okay. Okay, so here we can just see an example of it. Also, I forgot to mention, we call this Le Chatelet's principle. Le Chatelet was the guy that came up with this idea that we have reversible reactions that can be altered by changing the environmental conditions. Okay, or the conditions of the reaction, but still that equilibrium can be changed. Okay, an example of the temperature change. So we know that if temperature increases, it's going to favor the endo reaction. If temperature decreases, it's going to favor the exo reaction. So the dehydration of salt is going to require heat, and so the forward reaction is endothermic. To dehydrate something, to remove its water, you put heat into it. So you increase the temperature. It will favor the forward reaction. However, if we were to, an increase in temperature would therefore favor, yes, the creation of water and anhydrous sulfate. But if we were to decrease the temperature, okay, that would then favor the exothermic and the reverse reaction. And then there would be hydrated copper sulfate being made. So as we can see here, when we're talking about pressure change, okay, we said that an increase in pressure is going to favor the reaction or the side that has more molecules, and a decrease in pressure is going to favor the side that has less molecules. However, I just put this equation in here to show you guys what I'm talking about. These coefficient numbers, okay, they tell you how many molecules are created. So even though we have 2 molecules of reactants, we also have 2 molecules of products. So in this case, increasing or decreasing pressure won't make a difference. Okay, but if, let's say, this coefficient of 2 wasn't there, okay, if it was a different reaction and there was no coefficient of 2, then our forward reaction would have been favored if we increased pressure. Okay, because then we would have had 2 molecules to 1. But in this case, we have 2 molecules of products and reactants, and therefore it wouldn't change. Okay, I hope this makes sense, and I'll see you in the next lesson.